Tonight what we're going to be talking about is pressure. And pressure is defined as the amount of force exerted over a given area. And you can change the force by changing the speed of the particles or by changing the amount of particles that are running into a given area. What we're going to be focused on in this class is actually pressure events. And we've defined pressure events as the collisions that the particles have with the container walls. And each collision creates pressure. Pressure events that we're going to be studying are really only significant for gases, so we're not really going to be bothering with liquids or solids. How you draw a particle picture with a pressure event is you draw, this is an example down here, but another way that just to show you how to draw it is you can draw your particle and then your normal whooshy. And let's say, oh my gosh, I needed to do a pressure event for this. All you have to do is extend that whooshy and bounce it off the wall. You are always going to be extending the whooshy. You never are going to be going in different directions. For example, your whooshy would never be going that way, and then this would be your pressure event right here. Okay, because otherwise we've already defined that pressure events or whooshies are always in the past, telling where the particle came from, not where it's going. So this would not be a good drawing, whereas this would be. Some people like to then circle the pressure event so that they tell the teacher, hey, this is where my pressure event occurred. Atmospheric pressure is the pressure that's exerted by air particles. And what happens is that actually depending on the weather, meaning whether it's hot or cold, or the elevation, your pressure is going to change. A lot of times atmospheric pressure changes when you go up in elevation, there are less particles, and when you go down in elevation, there are more particles. The less particles you have, the less opportunities there are for pressure events, and the more particles you have, the more opportunities there are for pressure events. Therefore, when you are going below sea level, okay, where there's more particles, you're going to have more pressure. Whereas if you go above sea level, such as at Mount Everest, there's a lot less particles, so therefore you have less pressure events. This is how I would show that. If you look at the top, or if you look at the above sea level one, you notice there's only 3 particles, and therefore there's only 2 pressure events. Therefore, when you look at below sea level being 5, they have 4 pressure events, and that's just because of how many particles are actually seen. Just like with temperature, there are multiple units. For temperature, you have Kelvin, you have degrees Celsius, you have degrees Fahrenheit. And pressure is just the same. We have for pressure, the main 3 are kilopascals, which are abbreviated kPa. We have atmospheres, which are abbreviated ATM, and we have millimeters of mercury. And if you broke down millimeters of mercury, millimeters is abbreviated as mm, and mercury, if you looked on the periodic table, symbol is Hg. So that's where we get the symbol of mmHg. And a lot of times it depends on what science you're studying to see which unit of pressure you would use. In this class, we're going to use all of them, but commonly, if you were studying physics, you would use kilopascals. If you are studying chemistry, you would be using atmospheres. And if you were doing millimeters of mercury, you'd be studying meteorology, which is also weather. The conversions that you need to know, just like there are conversions between Kelvin and Celsius by adding or taking away 273, the conversions that you're going to need to know how to use is that 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 101.3 kPa. Okay? Just like with, if I said, hey, I ran a 5-kilometer race, it would be equal to 3.1 miles. If I said I had 1 atmosphere of pressure, I would also be saying that I had 101.3 kilopascals. They are all equivalent to each other. One question that you're going to need to know for your test is about balloon and their pressure. The balloon has the ability to change its pressure to equal the surrounding pressure. In a lot of the problems that you're going to be talking about, you're going to be changing the temperature or the volume of a balloon, but you're not really going to be changing its location. Therefore, because the outside pressure maintains the same, your inside pressure will maintain the same. So for balloons, you always want to think of it basically as its pressure is going to be staying the same as long as the atmospheric pressure is staying the same. You are also going to be expected to do for every statements. And just like in the past, you can come up with for every 1 atmosphere, there are 760 millimeters of mercury. For every 760 millimeters of mercury, you have 101.3 kPa. And for every 1 atmosphere, there is 101.3 kilopascals or kPa. You are also going to be expected to convert. Just like how you did it in the past, you're going to set up proportions. And so I know that I'm asked to go from 4.5 atmospheres to millimeters of mercury. So I'm going to set up my known 4.5 ATM, and I'm going to figure out how many millimeters of mercury there are. Now, off the top of my head, I don't necessarily know what the conversion is, but I do know that ATM will need to be on the top, and I do know that millimeters of mercury needs to be on the bottom due to ATM being on the top on the other side and millimeters of mercury on the bottom on the other side. So what I'm going to do is I'm going to look at my conversions, okay, which are right here, and I'm going to use those numbers. So I know that it's 1.00 ATM is equal to 760 millimeters of mercury, and now I'm just going to cross multiply and divide, and I get 3,420 millimeters of mercury. Rounded to the correct number of sig figs, which 4.5 has 2, be 1, 2. This number is going to stay the same because it is followed by a 2, so it would be 3,400 millimeters of mercury. Now you're asked to go from 420 kilopascals to ATM. So we're going to solve it the exact same way that we did the other side. So we're going to do 420 kPa is my known. I'm wanting to go to ATM, so I'm going to put it over X ATM. I'm going to set up my proportion. kPa is going to go on the top because it's on the top on the other side. ATM needs to go on the bottom because it's on the bottom on the other side. So I'm going to look at my conversions. I know that it's 1.00 ATM for every 101.3 kPas. Now I'm going to cross multiply, and when I divide, I get 0.241 ATMs, which rounded to the 2 sig figs found in 420. It's going to be 0.24 ATM. That one is going to drop off. All right, this is a key that you guys really need to know. STP, S stands for standard, T stands for temperature, and P stands for pressure. Okay, so STP stands for standard, temperature, and pressure. By me as a scientist saying that I am at STP, I've set conditions for my gases. STP is defined as 1 atmosphere or 273 Kelvin. Standard pressure, or the SP, would be the 1 atmosphere. Standard temperature would be the 273 Kelvin. Just like if I said I ran a marathon, everybody would know that I ran 26.2 miles. If I'm telling a scientist or a student in chemistry that I put my gas at STP, I am telling you its pressure is 1 atmosphere, and I am telling you that its temperature is 273 Kelvin. I am telling you the exact things. It's like me writing it out for you. Instead of saying 273, I just say standard temperature. Now, just because you're in 1 atmosphere, if for whatever reason the problem gives you it in kilopascals or another pressure unit in kilopascals or millimeters of mercury, you can use the ones that are found above and make those your standard pressure. So just because it says 1 atmosphere here, if you wanted to, you could write down 760 millimeters of mercury or 101.3 kPa. They are all saying the same thing. Just like if for whatever reason you need to be in degrees Celsius and I said it was at standard temperature, that is equal to 0 degrees Celsius. This graph, you guys will be generating during the class all of these relationships between pressure and volume, pressure and temperature, volume and or amount. You're going to be doing these in class. So from the labs, you can then fill out these notes. So for right now, you can skip this page and move on to the next one. Okay, the last one is KMT, and KMT is the kinetic molecular theory, or kinetic molecular theory. And what it does is it basically describes gases and gases behavior. So the first part of the KMT theory, okay, or kinetic molecular theory, is that gases are in constant motion, meaning that they never stop, that they move in straight lines unless they collide with something else. Okay, so only when they actually collide with something else will they change direction. Otherwise, they're going to continue going straight at all times. So how you draw that as a particle picture is you have your particle. It's always going to be going in a straight line unless, for whatever reason, that particle had bounced against a wall or ran into a wall or another particle. So for this instance, that particle was going in this direction, ran into this wall, and was forced to bounce off. So it created a pressure event. Gases also experience perfectly elastic collisions. An elastic collision is if I had a bouncy ball, okay, and I dropped that bouncy ball, it would always go, if it had a perfectly elastic collision, that bouncy ball would never stop bouncing. It would always bounce off the floor and bounce up to the exact same height that I dropped it at. Now, what happens is that some of the energy that is being released will go into the floor for friction, or it'll be transferred into other things. This happens with gases, but we tend to just try to ignore it because it would just be mind-boggling how to continue or do these math problems if we didn't say, hey, you know what, they experience perfectly elastic collisions. So what that means is when a particle bounces off one another, it has the exact same amount of energy before as after that collision. And so what you want to do for showing it as a particle picture, you're going to draw a particle bouncing off of one another, and they're just going to be changing directions due to running into something. All right, the speed is related to its temperature, and we've talked about this. So what that means is that the faster you go, the higher the temperature. The slower the particle is going, the slower the temperature. So what you do to show this is you draw a particle, and it has either one whooshy or two or three or four, but the more whooshies you have, the faster those particles are going, which means that it is going at a faster or a higher temperature. And then the last one is that pressure is related to the number and the strength of the collisions with the sides of the container. Number is based off of how many particles you have, and strength is basically how fast they are going. So in this one, what I'm showing is that this is one type of particle, okay, a situation, and I now added more particles, so therefore it has more pressure events. And the second one, this will have more pressure, the top one, because it is going faster than the bottom one. Okay. Now we're not really going to be concerned about this particular one in this class. We're going to be more concerned about this one, the number of particles affecting the pressure as opposed to the speed of the particles affecting the pressure. All right. Hopefully you understand pressure a little bit better and have a great evening.